えーっはいはい。私は、古賀先生です。ツイッターです。それで、ハッシュタグサスキンの QM で探していただければ、このページが出てきます。それで、コンパスに行けば、コンパスの中で、こういう、そうか。これを入れなきゃいけないね。コンパスの、ここに入れますと。ダメだ。コンパスのここに入れます。それで保存。どうだっけ。ページを確認で、ここに出てきます。それから、ブルーキャットに行きます。ブルーキャットにならないのはなぜ。ブルーキャットに行きます。それで、編集。それで、ここに入れます。これね。セーブ。で、下にも入れます。それで、更新と。いいかな。更新。はい。それから、これサスキンドのクォンタムメカニクスです。で、かつ、ここに PDF。PDF というところに行っていただくと、テキストボリューム3があるので、開けていただく。それから、回んないな。何ページだ ?45 ページぐらいかな。317ページからですと。で、クォンタムメカニカルディスクリプション。どこまでやったの ?317 ページかな。ここから読んでみようか。Quantum mechanical description. Now let's return to our microscopic version of the weight and spring system. Let's say no bigger than a single molecule. At first, this seems ridiculous. How could we ever build a spring that small? But in fact, nature provides all sorts of microscopic springs. Many molecules consist of two atoms. For example, a heavy atom and a light one. There are forces holding the molecule in equilibrium with the atoms separated by a certain distance. There are forces holding a molecule. When the light atom is displaced, it will be attracted back to the equilibrium location. The molecule is a miniature version of a weight and spring system, but is so small that we have to use quantum mechanics to understand it. Having worked out the classical Lagrangian, let's try to build a quantum mechanical description of our system. The first thing we need is a space of states. As we've seen, the state of a particle moving on a line is represented by a wave function psi x. There are many possible system states, and each one is represented by a different wave function. A function psi x is defined in such a way that psi star psi is the probability density, the probability per unit interval to find a particle at position x. Psi star psi equal px. In this equation, p of x represents the probability density. We now have a sort of kinematics, a specification of what the system states are. I forgot the Japanese word for kinematics. Undogakuね。はい。Can psi be any function at all aside from the requirement that it must be continuous and differentiable? The only extra condition is that the total probability of finding the particle at any position must be 1. So this is a normalization. Integration from minus infinity to infinity, psi star psi with respect to x is 1. This is a normalization. This would not seem to be much of a restriction. However, or whatever the right-hand side of this equation is, we could always multiply psi by some constant to make the integral equal to 1 unless the integral is either 0 or infinity. Since psi star psi is positive, we don't have to worry about 0. Since psi star psi is positive, we don't have to worry about 0, but infinity is a different matter altogether. There are lots of functions that would make the integral in equation 1010 blow up. The condition for a sensible wave function thus include the requirement that psi falls to 0 first enough. The conditions for a sensible wave function thus include the requirement that psi falls to 0 first enough that the integral converges. Functions that meet this condition are called normalizable. Sensible.賢明な。センシブ、分別なる、資料のある、賢明な道理にかなった。Sensible wave function thus include the requirements that psi falls to 0 first enough that the integral converges. Functions that meet these conditions are called normalizable. There are two questions we might ask about our harmonic oscillator. How does the state vector change as a function of time? To answer this question, we need to know the Hamiltonian. What are the oscillator's possible energies? These are also determined by Hamiltonian. So, to know anything useful, we need the Hamiltonian. Fortunately, we can derive it from the Lagrangian. And I will remind you how in a moment. But first, recall that the canonical momentum conjugate to x is defined as partial L partial x dot. This is canonical momentum conjugate to x. Combining this with equation 10.5. I think 10.5 should be like this. L equal 2 1 m x dot square minus 1 half. I think this is wrong. It goes like this. L Lagrangian was 1 half x dot square minus 1 half omega square x square. That was Lagrangian. So then we plug this in to this equation. We obtain P equal x dot. Using a straightforward definition from classical mechanics, we find that Hamiltonian for harmonic oscillator is H. This is called Legendre transformation. H is px dot minus L, where P is the canonical momentum conjugate to x, and L represents the Lagrangian. We could work directly from this definition, but instead we will take a shortcut. Because the Lagrangian is the kinetic energy minus the potential energy, the Hamiltonian is the kinetic energy. I think a better way to say is while the Lagrangian is the kinetic energy minus the potential energy, the Hamiltonian is the kinetic energy plus the potential energy. In other words, the total energy, the Hamiltonian for the oscillator, can therefore be written as H equal 1 half x dot square plus 1 half omega square x square. So far so good, but we are not quite finished. We've expressed kinetic energy in terms of velocity. In quantum mechanics, however, we need to represent our observables as operators, and we don't have a velocity operator. To take care of this, we will have to recast things in terms of position and canonical momentum, which does have a standard operator form. Rewriting the Hamiltonian in terms of canonical momentum is easy because P is del x partial L partial x dot equal x dot, which allows us to write H equal 1 half P square plus 1 half omega square x square. Footnote 2. We don't need to use the summation sign because there is only 1 degree of freedom. Okay, that's the classical Hamiltonian. We can now turn it into a quantum mechanical equation by reinterpreting x and p as operators defined by their action on psi. As we've done before, we will use the boldface symbols x and p to distinguish our quantum mechanical operators from their classical counterparts, x and p. From previous lectures, we know exactly how this operator works. X just multiplies the wave function by the position variable, and p takes the same form it does for other one-dimensional problem. The position operator is just x. Momentum operator is this one. But I would recommend you to remember like h bar over I. This is same. It's easier to remember this way. I like this way better. So now we can figure out the action of the Hamiltonian on a wave function by letting p act twice on the wave function. This is the same procedure following in lecture 9. In other words, h acting on psi x is 1/2 minus IH bar partial x minus IH bar partial psi partial x plus 1/2 omega square x square psi, or h acting on psi goes like minus h square divided by 2 partial psi partial x square plus 1/2 omega square x square psi omega square x square psi. We are using partial derivatives because in general psi also depends on another variable, time. Time is not an operator. Time is not the operator, and does not have the same status as x. But the state vector does change with time, and we therefore treat time as a parameter. The partial derivative indicates that we are describing the system at a fixed time. Section 10.3. The Schrödinger equation. Equation 10.12 shows how the Hamiltonian operates. How the Hamiltonian operates on psi. Now, let's put it to work. As we said in the previous section, one of its jobs is to tell you how the state vector changes with time. So let's write out the time-dependent Schrödinger equation, which is I partial psi partial t equal 1 over h bar h psi. Substituting for h using 1012, we get I times partial psi partial t equal minus h bar divided by 2 partial square psi partial x square plus 1 over 2h bar omega square x square psi. This equation says that if you know psi, both the real and imaginary part, at some particular time, you can predict that it will be at you can predict what it will be at a future time. Notice that the equation is complex. It contains I as a factor. This means that even if psi starts out being real valued at time t equals 0, it will very shortly develop an imaginary part. Any solution psi must therefore be a complex function of x and t. You can solve this equation in a number of ways. For example, you can solve it numerically on a computer. Start with a known value of psi x and update it slightly by calculating the derivative. Once you have the derivative, calculate how psi x change in a small increment of time. Then add this incremental change to psi x and keep doing it over and over. It turns out that psi x will do some interesting things. It will move around somehow. In fact, under certain circumstances, it will form a wave packet that moves around very much like a harmonic oscillator. Chapter section 10.4 Energy Levels. The other thing you can do with the Hamiltonian is calculate the energy levels of the oscillator by finding the energy eigenvectors and eigenvalues. As we learned in lecture 4, once you know these eigenvectors and eigenvalues, you can figure out the time dependence without solving any differential equations. You can figure out the time dependence without you can figure out the time dependence without solving any differential equation. Because if you have eigenvalue, so once you have eigenvalue for h, so let's call this En. Then your wave function and eigenvector. Let's see if your eigenvector is n. Then time dependence. Time dependence goes like exponential minus IEN divided by h bar times t times n. This is the time dependence. So n comma t. Let's see. You can write it this way. This is like comma 0. Yeah. So time evolution can be written easily if you have eigenvectors and eigenvalues. So you can figure out the time dependence without solving any differential equation. That's because you already know the time dependence of each energy Eigenvector. You may want to review the Schrödinger's cat recipe we gave in section 4.13. For now, let's concentrate on finding the energy eigenvalues themselves using the time-independent Schrödinger equation. H psi e equal E psi e. The subscript E indicates that psi e is the eigenvector for a particular eigenvalue E. This equation defines two things: the wave function psi e and the energy level E. Let's make things less abstract by expanding H using equation 1012. So 1 minus h bar square divided by 2 partial square psi e divided by partial x square plus 1/2 omega square x square psi e equal E psi e x. To solve this equation, we must find the allowable value of E that permit mathematical solution. Second, we find the eigenvectors and possible eigenvalues of the energy. This is very simple. So maybe number one, we find allowable value of E. Second one, we find the eigenvectors. So this one is find possible eigenvalue of the energy was already done in the first. Anyway, we find eigenvalues of the energy and we find eigenvectors. And unfortunately, this is a little trickier than you might think. There turns out to be a solution to the equation for every value of E. There turns out to be a solution to the equation for every value of E, including all the complex numbers, but most solutions are physically absurd. Physically absurd. If we just start at some point and solve the Schrödinger equation by making little incremental steps, we will almost always find that psi grows or blows up as x becomes large. In other words, we may be able to find solutions to the equation, but only very rarely will we find a normalizable solution. If we just start at some point and solve the Schrödinger equation by making little incremental steps, we will almost always find that psi x grows or blows up as x becomes large. In other words, we may be able to find solution to the equation, but only very rarely will we find a normalizable solution. Okay, so this is the equation we have to solve. Yeah. Okay, here what we can do is following. We can rewrite this to partial square psi x partial x square equal e minus 1/2 omega square x square psi x. Here is the minus. Yeah. So that means I think we need, let me explain you a little bit. So let's make this part, just for simplicity, let's make this ax. Okay, so the equation we have is following. Whiteboard. The equation we have to solve is the following. We have partial square psi. I omit e. Okay, we have partial square psi x. We have partial x square equal a x psi x, and we also omit t because we consider psi xt at a given fixed time. Okay, so then we just assume this way. So we have this is x. We start at any point. Let's do it like x0. Then this is psi. So we have some point psi x0. We also assume we also know this point x0 plus del x. We know psi x0 plus del x. Also here x0 minus del x. We know psi x0 minus del x. Okay. Let's assume we know these three. Yeah, we know this one, this one, this one. Then we can see this one. Partial square psi partial x square is more like this one. You have partial psi x0 minus plus delta x minus psi x0 divided by delta x minus psi x0 minus psi x0 minus delta x divided by delta x divided by delta x. This is more like second derivative. Partial square psi partial x square can be written like this if delta x is small. Sufficiently. We usually use the word sufficiently. Sufficiently small. Delta x is sufficiently small. Then we will see. This is more like this. This is equal psi x plus delta x minus 2 psi x 0 minus x 0 minus delta x divided by delta x. Yeah. So what shall we do? This is ax psi x. This is more like ax0 psi x0. Yeah. Oh, there is a square. This is a square. And I think this has to be plus. I think this is how we do. We do here. These two. We assume these two. We know these two. And we try to find psi x0 plus dx. Okay, this is what we should do. So this is what we have to find. This one we have to find. Okay, so then we can solve the equation for this. So we have psi x0 plus delta x equal to psi x 2 plus you can do plus a x0 delta x square psi x0 minus, I think this is minus psi x0 minus delta x. Is this correct? I think this is correct. So if we know 2 points, this and this, then if we have a Schrödinger equation to solve, or if you put any energy value here, any value for energy, if you have 2 points inside, then we can find third point. This is the third point. Yeah, if we know 1, 2, then we know 3. And we can repeat the same way. If we have 2, 3, then we obtain 4. Then if we have 3, 4, then we have 5. So in this way, we can obtain psi, wave function psi, for any value of E. That's what he says. It turned out to be a solution to the equation for every value of E, including all the complex numbers, but most solutions are physically absurd. If we just start at some point, we actually need 2 points. 2 points, and solve the Schrödinger equation by making a little incremental step. That's what I did here. We make a little incremental steps. We will this is not always, almost. We will always find the solution, this is okay. We will almost find that psi blows up at x become large. In other words, we may be able to find a solution to the equation, but only very rarely will we find a normalizable solution. Okay, so in this way, we can find some solution easily. So if we have psi x0, this is psi x0, then if we have psi x0 minus delta x, so then this is 1, 2. So we can find number 3 point and number 4 point. So we can easily find. But this function almost all the time just blow up. So it's very difficult to find a normalizable solution. Okay, I think I can stop. 323. So, next time you can see. Oh my god. So, next time you can see there is a SusskindQM see there is tonight. The next time is tonight, 9 o'clock. Then please select the time you can join after tonight's session, so which is tomorrow. So I created this. Okay. I can create more later, so you can select the time you like to join this session. Okay, see you.